Okay, picture this. You're, out in the field, maybe doing some bird watching, and you want to use an app to identify this, like rare bird you spot, but your phone's low on battery. This kind of real-world problem is what today's deep dive is all about. You shared a research paper titled COA, Fast Carving of Mixture of Experts for Efficient LLM Inference. And it's tackling a big challenge in AI, making these powerful large language models way more efficient, but without sacrificing their capabilities.
Yeah, I think what's really exciting about this approach is that it could make powerful AI accessible, even on devices with limited resources. It's not just about identifying birds, though. Think like medical diagnoses in remote areas or real-time translation, even personalized learning tools, all running smoothly on your phone or, a low-power device.
Right, right. Okay, so we're talking about LLMs, those massive AI models that can, you know, write poems, translate languages, and answer your questions in a seemingly like human-like way. But they're also known for being resource intensive. What makes them so power hungry in the first place?
Well, I think the core issue really lies in their sheer size. LLMs can have billions of parameters, which are kind of like the connections between neurons in a brain. And traditionally, even for a simple task, all these parameters are activated, which leads to a lot of computational overhead. It's like using a giant supercomputer to solve a simple math problem.
Yeah, I get it. So it's like trying to, run a marathon when you only need to walk to the corner store. This research is trying to make those AI models work smarter, not martyr. Before we jump into their solution, though, can you explain this mixture of experts architecture that the paper keeps mentioning? I'm not sure I fully grasp it.
Okay, sure. Imagine a team of specialists, each with expertise in a specific area. Instead of like calling upon every specialist for every task, you'd only activate the relevant experts, right? This targeted approach streamlines the process and saves resources. That's essentially what MoE or Mixture of Experts architecture is all about.
Okay, so instead of using the entire massive LLM for everything, we could divide it into specialized units and only activate the ones needed for a particular task. Sounds promising, but there must be a catch, right?
Yeah, you're right, there is. Building these specialized MoE models from scratch usually requires a ton of data and computational resources. It's like assembling a team of, world-class experts and then having to train each one from the ground up. It's time-consuming and expensive.
And this is where CMOE comes in. It somehow bypasses that intensive training process.
Exactly. CMoE, or fast carving of mixture of experts, takes a different approach. Instead of training a new MoE model from scratch, it carves one out of an existing, like, fully trained LLM. It's like taking a fully formed, highly complex brain and reorganizing its neurons into, like, specialized teams.
So instead of building a new team of experts from scratch, CMOE identifies the specialists that already exist within the massive LLM. That's a pretty clever shortcut. I'm curious, how does it identify those specialists?
Well, CMoE distinguishes between two types of experts: shared experts and routed experts. Shared experts are like our, general knowledge things we use constantly. And routed experts are those specialized skills that are only needed occasionally.
So shared experts are always active, like the core functions of a computer, while routed experts are called upon only when needed, like specific software programs.
Yeah, that's a good analogy. And what's really fascinating is how CMoE figures out which expert is which. It analyzes how often each neuron in the LLM is activated, kind of like giving each neuron a score based on how frequently it's used.
So the neurons that are activated frequently, the ones with like high scores, they become shared experts because they represent common knowledge or frequently used skills.
Exactly. And here's where it gets really interesting. The research found that the distribution of neuron activation is highly skewed. That means a small percentage of neurons are doing most of the work.
Okay, hold on. Why is that significant? What does that tell us about the potential for efficiency?
Well, it suggests that there's a huge opportunity to optimize these massive models. Imagine if we could, identify that small percentage of neurons doing the heavy lifting. We could potentially, like, shrink these models dramatically without losing much performance.
So CMOE is essentially identifying those key players and making sure they're always on the field while, strategically calling upon the specialists only when needed. It's like streamlining a massive organization, identifying the key personnel, and optimizing their roles. But how does it actually decide which specialist to activate for a specific task?
Right, that's where the routing in CMoE comes in. It uses a clever mechanism derived analytically rather than through, like, extensive training to decide which routed experts to activate based on the task at hand.
Wait, so they don't need to train the routing mechanism separately? That seems like a major time saver.
Absolutely. This means CMoE is, readily usable without the need for mountains of data and training time.
So CMOE is carving out these specialized expert teams from existing large language models and activating them on an as-needed basis. Sounds like a pretty elegant solution, but how well does it actually work in practice? Does it really deliver on the promise of, efficiency without sacrificing accuracy?
Yeah, that's the key question, right? The researcher put CMOE to the test, evaluating its performance on two key aspects of language models. First, they looked at language modeling itself, essentially how well the model understands and predicts language.
So, for example, if you gave it the beginning of a sentence like, the quick brown fox, could it accurately predict the next word, like, jumps?
Exactly. And to measure that, predictive ability, researchers use a metric called perplexity. Think of it like a measure of how surprised the model is by the text it's processing. The lower the perplexity, the better the model is at predicting language, making it sound more fluent and natural.
Okay, so lower perplexity means the model is like less confused by the language it's encountering. What did they find in terms of CMOE's perplexity? Did it hold up against those resource-intensive traditional LLMs?
Well, even without any additional fine-tuning, CMoE achieved a respectable perplexity score, meaning it had a decent grasp of language right out of the gate. But what's really impressive is that with just a bit of fine-tuning, it actually surpassed existing methods for making LLMs more efficient.
So not only is it more efficient in terms of, resource usage, but it's also potentially more accurate than other optimization techniques. That's a pretty compelling combination.
Absolutely. But language modeling is just one piece of the puzzle. They also tested CMoE on downstream tasks, specific jobs that LLMs are often used for, like answering questions or summarizing text.
So things like asking it to like summarize a news article or translate a document from one language to another.
Exactly. And in these tests, CMoE really shined. It consistently outperformed traditional MoE models on various downstream tasks, demonstrating its ability to not only understand language, but also apply that understanding to solve problems.
Do you have like a specific example of how much better it performed?
Sure, one of the datasets they used was SciQ, a collection of science questions. On this dataset, CMoE achieved an impressive 76.59% accuracy after fine-tuning. In comparison, a traditional MoE model only reached 21.2%. That's a massive difference.
Wow, 76.59% accuracy while using significantly fewer resources. That's starting to sound like a game changer, but I'm curious, you mentioned fine-tuning a couple of times. Can you explain what that means in this context?
Sure, think of it like fine-tuning a musical instrument. Even if the instrument is, well-crafted, you still need to adjust it to produce the desired sound. Similarly, even though CMoE is carved from a pre-trained LLM, some adjustments are needed to optimize its performance for specific tasks.
So even with this clever carving approach, there's still a need for some level of like customization.
Yes, but the key point is that the amount of fine-tuning required is significantly less than what's typically needed for traditional MoE models. This translates to, faster development times and lower computational costs.
Got it. So less time and fewer resources to get those impressive results. It seems like there's a lot to be excited about here, but every breakthrough usually comes with its own set of challenges and limitations. What are some of the things we should be like cautious about when it comes to CMoE?
That's a great point. It's important to remember that this is still, relatively new research, and there are open questions to address. One thing the researchers themselves highlighted is the need to further investigate the impact of training data.
So even though CMoE is carving from an existing LLM, the quality and diversity of the data used to train that original LLM could still influence the performance and potential biases of the carved model.
Exactly. It's like inheriting a toolbox from someone else. The tools themselves might be well made, but if the original owner only used them for like specific tasks, they might not be suitable for everything you need.
That makes sense. It highlights the importance of data curation and responsible AI development, even when using these efficient carving techniques. Are there any other limitations or like potential downsides to consider?
Another interesting question the researchers raised is whether this focus on efficiency might come at the expense of accuracy for certain, like, complex tasks.
So while CMoE performs well on many tasks, there might be some scenarios where the The traditional resource-intensive approach still reigns supreme. It's like choosing between a nimble sports car and a powerful truck. Each excels in, different situations.
That's a good analogy. More research is needed to fully understand the trade-offs between efficiency and accuracy in different contexts. But even with these open questions, the potential of CMOE is undeniable.
It certainly seems like it. Now, you mentioned earlier that the researchers themselves have highlighted some areas for future exploration. What are some of the things they're hoping to, delve deeper into?
Well, one area they're particularly interested in is exploring different methods for grouping and selecting those expert neurons. They primarily focused on activation rates in this study, but there might be other factors or combinations of factors that could lead to even more efficient and specialized expert teams.
So it's like saying, hey, we found a great way to assemble these expert teams, but maybe there's an even better way to do it. Maybe by looking at not just how often a neuron is used, but also what kind of information it processes, we could create even more specialized and efficient teams.
Precisely. Another avenue for future research is exploring how CMOE can be applied to different types of LLMs beyond the ones used in this study. They used a specific family of LLMs called LLM models, but there are many other architectures out there.
So while CMoE has shown, great promise with LLM models, we still need to see how well it translates to other types of LLMs. It's possible that some architectures might be more amenable to this carving approach than others.
Absolutely. And then there's the exciting possibility of combining COE with other model compression techniques. There are other methods for making LLMs more efficient, like pruning away unnecessary connections or quantization, which reduces the precision of calculations.
So it's like asking, can we make these already efficient CMoE models even leaner and meaner? By layering on other optimization techniques, if we can combine the strengths of different approaches, we might achieve even more dramatic improvements in efficiency.
Exactly. And perhaps the most exciting prospect is seeing how CMOE will influence, real-world AI applications. If we can make LLMs more accessible and affordable, it opens up a world of possibilities for, like, personalized AI on edge devices, and AI for everyone, regardless of their computational resources.
It paints a picture of a future where powerful AI is no longer confined to uh, massive data centers or like expensive devices, but is readily available to anyone with a smartphone or even a low power device. It's a future where AI can truly empower individuals and communities around the world.
That's the vision. And while there are still, challenges to overcome and questions to answer, this research takes a significant step towards making that vision a reality.
It's been fascinating to delve into this research with you. You've shared a lot of insights from the paper, but I'm curious what personally stood out to you the most. What was your big haha moment?
Honestly, what struck me most was the sheer elegance of the CMOE approach. It's such a clever and intuitive solution to a complex problem. It's like they found a way to make these, massive LLMs think smarter, not harder.
I completely agree. And the fact that it achieves this efficiency without sacrificing accuracy is truly game changing. It makes me wonder if CME is so good at optimizing resource allocation within AI models, what other areas could benefit from this approach?
Now, that's an intriguing question. Could we apply similar principles to, like, optimize energy consumption in data centers, streamline logistics and supply chains, or even improve decision-making processes in large organizations?
It's fascinating to think about how the core concepts behind CMOE, selective activation, resource allocation, and dynamic specialization, could be translated and applied to other fields and industries. This research might just be the tip of the iceberg, sparking a wave of innovation in efficiency optimization across various domains.
Yeah, it's a great reminder that sometimes the most brilliant solutions come from, thinking outside the box and finding ingenious ways to work smarter, not harder.
Yeah, it's like a ripple effect of innovation spreading outwards from this one breakthrough in AI. It is inspiring to think about like the potential impact it could have, across various fields. But before we get too carried away, let's bring our focus back to the research itself. If you could ask the researchers one question about CMOE, what would it be?
Oh, that's a great question. If I had the opportunity, I'd probably ask them about their vision for the future of LLMs in light of CMOE. Do they believe this shift towards, efficiency will fundamentally change how we design and train these models?
That's a fascinating thought. Will we see like a new generation of LLMs that are built from the ground up with efficiency in mind? Or will we continue to, refine these carving and optimization techniques to make existing models more efficient?
Right. It's like asking whether we'll see a new breed of cars, designed for fuel efficiency from the start, or if we'll keep making existing cars more fuel efficient through like add-on technologies. I think both approaches have their merits.
Yeah, and it's likely that both approaches will play a role in the evolution LLMs. But I wonder, could this focus on efficiency also change our very understanding of what intelligence means in the context of artificial systems?
That's a profound question. For so long, we've equated AI intelligence with size and complexity. The bigger the model, the more intelligent it seemed. But CMOE challenges that assumption.
Right. It suggests that intelligence might not be about, brute force computation, but about the ability to strategically allocate resources, identify and leverage relevant knowledge, and adapt to different tasks with minimal overhead. It's a more nuanced and perhaps even more human-like conception of intelligence.
It's a fascinating shift in perspective, and one that could have profound implications for how we develop and interact with AI in the future.
Well, on that note of pondering the future of AI, I think it's time to wrap up this deep dive. We've explored the technical intricacies of CMOE, its potential advantages and limitations, and its broader implications for various fields.
Yeah, it's been a thought-provoking journey, and I hope our listeners are leaving with a deeper understanding of this, groundbreaking research and its potential to reshape the landscape of AI.
And perhaps even a few lingering questions and a desire to explore this topic, further. If you're eager to learn more, you'll find links to the research paper and other resources in the show notes.
Right. Remember, the learning doesn't stop here. We encourage you to, delve deeper into the source material, ponder the questions we've raised, and perhaps even come up with some of your own.
This deep dive might spark a new idea, a research direction, or even a change in perspective that could contribute to the ongoing evolution of AI. Until next time, keep exploring, keep questioning, and keep diving deep into the world of knowledge. 20 Tika 1.